So, Julia, what is Julia? Julia is a scientific computer programming language like Python. It brings the high level interpreted and the low level compiled language together to form this one. It offers the high performance, and for example, the performance is comparable to C and the Fortran, without sacrificing the simplicity and program productivity. It is simple and Python, it's very easy to understand the meaning from the code. So Julia has a powerful inbuilt package manager, and this manager can help you to install and manage all their dependencies. And Julia is a rich ecosystem, has a rich ecosystem for libraries for scientific computing. We can come to this episode in the afternoon. And actually, not only for scientific computing, but also extensive applications in data analysis and the visualization, and also the machine learning. This time, Julia is comparable to Python, but it's much faster than the code if you write in Python. I will come to this motivation part. In this introduction to Julia, today we're going to cover this introduction to Julia. In this part, we'll cover the basic syntax of Julia right here, and also what is and also special features of Julia, development in Julia, and also scientific computing ecosystem in Julia. So in the following 3 days, we will cover to the Julia HPC. We have the following. So come to ECCS to get more info if you're interested in Julia, and we will have a follow-up workshop about Julia for high performance data analysis, which is arranged in February. So I will share this info with you later. Yes, let's talk about the motivation why we're going to use Julia. So why Julia was created? It has been from the developer, why we created Julia. And following this link right here, it was addressed that we need a language that is open sourced. It should be fast and it should be probably easy to understand. Yes, I covered everything right here, and I'm going to read the word by word so it can come this. So Julia, the intention is that they want to keep Julia as simple as possible and as fast as possible. So some features about Julia. So the first one is about the speed. If you make a comparison right here, you can see that C is the reference right here. You can see we take C as a reference, and for this multiple applications, for example, iterative pi summation, matrix multiplication, matrix statistics. These are the benchmark from Julia. Everything is quite close to C. In some cases, it's faster than C. Whereas Python is right here. For some applications, Python is okay, but in the most cases, the performance for the code written in Python is somewhat slower than that written in Julia. Suppose that you can write the performant code. Yes, and also some other programming language, like say R is here, MATLAB is here, Java is here, Fortran, Go. You can see Julia is quite competitive at lots of aspect for this programming. So why Julia was proposed? It's going to solve this two language problem. I suppose that you in the answering questions, I saw that some were familiar with the C, Fortran, and the Python. This is good, and both these programming languages has their pros and cons, and you might come to some ways that for some code, for example, the code writing in Python, the performance is quite slow. I need to rewrite some part using C or Fortran, so that to speed up the calculation. This always happen, and actually in the project, some code It's a combination of the code written in C, in Julia, Python, assume that Julia is used, and also sometimes Rust. We always come to the sort of translation of all this code into a machine code, machine instructions, or can say assembly code to get the executable file. But actually, the precise of the translation from different programming language to the executable code, file is different depending on the specific type of the programming language. If it is interpreted language such as Python and R, the translation will take place line by line, as you know this. And for others, for example, of C or C++ or Fortran, the translation were performed by the compiler before running the program. So that's compare everything to get the executable file before you run the simulation or calculation. Both interpreted and the compared language, they have their pros and cons. For interpreted language such as Python, the code is quite easy to read and write. It's, at least it's understandable to the human. And then there's no necessary for developers to care about the variable types and the size of, for example, the array matrix. So it leads to kind of high productivity for the developers. No need to care about something at the low level. For interpreted languages, for example, C, C++, and their performance is much better than the code written in Python or the other high level language programming, because the compilers can perform optimization during the code translation. This is the true language problem. For compiled language, they can achieve fast calculation, but the compilation is somewhat difficult. For interpreted, it's very easy to understand, it's easy to use, but the productivity may be is quite high, but the performance is not so high. So Julia was proposed to solve this kind of true language problem. Yes, compatibility in so in right here. So in many ways, Julia's looks like an interpreted language, as the code is usually interpreted line by line. But before, at the specific part for before the function was executed for in the Julia code, Julia's compiler will compile the function using the just-in-time technique, which means that this technique will get the flexibility. You can get the code, flexibility of an interpreted language, and the performance of the compiled language will be much faster than the translation line by line. Yes, I prepared some discussion. Let's come to this, back to this later. And also another feature of Julia is composability. So Julia is highly composable, which means that if you have multiple packages independently developed by Julia, you can use these packages together in your project to avoid the develop them new script or new packages from the scratch. And here is an example about the combination of differential equation. The GL is the package developed using Julia, and another one is the measurement of GL. We are going to combine these two packages to solve this pendulum equation like this. It is the right here of the code. We just use the usage of these two packages is quite easy. You can load these two packages and then use this one differential equations, measurement, and we are going to use this plot package to visualize these results. Yeah, from the code example below here, you can see that these two packages to save the to solve this equation, you can get exactly the same answer. It's exactly the result as that from the numerical calculation, which means that Julia is quite robust. They can combine using multiple packages developed using Julia. It can achieve the same result as that from the numerical calculation. But Julia is not universal. It has some drawbacks, and we also can provide some workaround how to avoid these drawbacks. For example, uh, if you are the first time to use Julia, times maybe somewhat maybe slow because uh, the script needs to be installed and launched. So the first time means that it takes more time for the running. And also this also means that for if you have quite a small script, it takes longer time than you expect. So if I say that Julia is not suitable for quite a small script, but the possible way that we can have a long script, you can put everything in the script, and you can also use this package compiler package. This is our package to create a precompiled package environment, including these libraries and their dependencies. Put everything there, something like a container, and so that is this one can be used if you copy paste to the different HPC clusters. You can reuse this. That's you can just avoid the slow problem when you first time to run this code. Ecosystem. We all know that if you are familiar with Python and R, we can have a quite a good ecosystem, and the developers worldwide we're going to make a contribution. But for Julia right now, there are less materials for R than R and Python. Sometimes maybe not easy to find the suitable packages to tackle your problems, but you can also directly use packages right in other programming languages. For example, uh, the the package right in Python and Fortran and C, because Julia has a very good interfacing to this programming language. And I will cover this aspect in the following episode and how to interface Julia with C, with Fortran, and with Python. And another thing is that if you are quite familiar with Julia after this workshop, why not rewrite some part of your code using Julia, and you can make this as a small project if you like. Um, yes, and for something like a rapid package evolution, you can use the package manager and to manage the dependencies of some Julia packages so that you can get all your packages and their dependencies updated in when you run your project. And last drawback is maybe the large memory footprint, and yeah, this is the thing for the Julia. In this uh, introduction to Julia programming, you will learn the basic syntax of Julia and what's the difference of Julia compared with other programming language, for example, C, Python. And we have also talked some features of Julia and some uh, packages available right in Julia so that you can use these program packages to in your project. And two lesson materials right here we have. The first one is Julia for high performance scientific computing. We are going to use this one in the following 3 days. And another one is Julia for high performance data analysis. We have arranged this workshop in the next February. So you can come to the EuroCC's website to check the latest info right there and for the registration if you are interested on this workshop. Yes, this is the motivation. Hope that you can get something on what is Julia and why we're going to talk about Julia. Let's move on to the second part, motivation right here. Introduction to Julia syntax. I will right here. Yeah, in this episode, I'm going to cover some basics of Julia syntax and how to run the Julia code and how to run the Julia script. We have some we cannot cover all this this part, but there is a video to cover this 300 pages book on Julia. So you can take time to watch this video and for maybe a thorough understanding of Julia. If you come from other programming language, for example, MATLAB, Python, and C or Common Lisp, you can take a look at this page and which lists some common features and the difference of Julia with this programming language. Yes, how to run Julia? Uh, let's take a moment. If you okay, let's come back to this thought. Lumi, I'm going to using this one to share my screen right here. Oh, which one you can see right now? Let me. Which screen can you see right now? Another double web browser screen. The right one is login to Lumi, right? Or
It, it says go to login.
okay, go to login. Great. This is the one I will try to have a short demo on how to log into Lumi and to show this programming environment right there. If you can access Lumi, it is quite good, and you can just watch my login. Otherwise, you can try to log in later. I come here. This is the Lumi csc.fi/public. This it is right here. I hope that you know how to access to log in Lumi via the web interface right here. Yes, my access ID and password thing. X. Yes, I'm coming to Lumi. Which one I'm going to use? I'm going to use the login node shell. There is an app called Julia Jupyter, but this one is we got some error right here, so we're not going to use this one. I'm going to use login node shell and to show you how to. Yes, it is here. Quite fast. Yes, this is the way we are in Lumi. Or where am I right now? During the handle accesses, you can come to this directory, cd scratch project 465001311. Yes, I'll just show this later, but this is just for the demo. And you can make your own directory right here. And how to download these modules, and you can follow here. This is the module use app use local CSC, and then this module files. Yes, and then module load Julia. If I type Julia, okay, check dash dash version. Yes, 1.11.2. If I type Julia, then I'm coming to this REPL environment. This is the default programming we're going to use. If you use the terminal for this for the programming, yes, this is the default mode. You can see if I print something, print, then for example, I type a string right here. Yes, it works. And if there are multiple typos, if I want to get come to the help mode, I type a question mark. You can see what changes right here. It comes to this help mode like this. And if I type backspace, I come to the Julia mode. And if I come to use semicolon, not here, you can see I come to the shell mode. Like for example, L. I will see what is here. Okay, that's right here. Oh, no, directory type. Okay. And this is the path to the directory. And I want to get it back to Julia mode, backslash. And this is the Julia mode. And I want the package mode. I have to use the square bracket right here. You can see this and come to the package manager mode and see how can I get this. Here you can add some packages and you can update your packages and back to the real mode. And if I want to get some help, and for example, I want to get a question mark type of. What is type of in the Julia? They can get this result. Type of is a function like this. And for example, we have a variable like this, and the type of, and then this variable, it can get this its direct type from here. Yes, this is the REPL programming environment right here. And we can also to use the Jupyter Notebook for this, but right here at Lumi, we cannot use this. So I will show you how to use that from this computer. Yes, right here. Here I have this launched this from the Anaconda. I have installed this iJulia. It can be used as the IDE right here. I click this one, and here I use the Julia versions 1.10 as for the interpreter. Let's see. Yes, it works. Then let me to use this to the as the left part, and this one to be the right part. I will have some demos right here. Okay, back for the review. I have talked about Julia mode and the type question mark. It can come into the help mode, and the type semicolon. It can come to the shell mode, and the type this bracket square bracket. It can come to the packing mode, and yeah, try to get familiar with this programming mode later. And here I'm going to just show how can we run this script from the left side. Left part is the Jupyter Notebook right here. So basic syntax. Basic syntax is the define define these variables and some run this basic arithmetic calculation and to get some specific result from these variables. For example, here is some form about the arithmetic calculation, the addition, multiplication, and take the power 2 power 3 and the square root and the float. This is the and also the remainder. This is quite basic for the mathematics. And there's something quite interesting I need to show you. If I type here to get the 10 with the power of 19, you can see that it gets the one with minus. This means this the integral overflow means something wrong. So how to solve this? You can either use the scientific way for to this one, or can use the big 10. We can come to this later about the special features of Julia. So this time we can get the correct results. And we can also have some complex numbers. For example, pi is the aim. This is for the imaginary part of this complex number. And also we can do them arithmetic calculations following this more. And then we, to check the type of all these variables we defined right here, we can use type of. Minutes ago, I show you how to use this one. For example, here, if we define a variable like this, a point 3, 2.3, like this, and type of a, see what is the type of a, it's a float 64. It's a float type, and if we keep this a is equal to, and then it's integer type, yes, then we can have lots of types like this. Scalar type, float type, integer type, Boolean type, and also complex type. Complex means a complex number. This is quite commonly used for the scientific computing part. And we can also define the string. And here I use the print. This is the string test Julia. This is a string type. And besides, we know the type of this variable, we can also to see the supertypes and also subtypes. For example, if we say subtypes of this A, now A is the integer type. We'll see subtype, what is, oh, error. This might be the bottom one. This is the supertypes. What is type? Int 64. No method. Super type. Usually it is. Give me a sec. 1, 2, 3. Top level unit. Oh, no method matching this int 64. Okay, if we type integer. Yeah, it's the super type. It is real. If we come to this super types, we can get a list of super types. It means integer, real, and the up real is number than any. Yeah, this is how to get the types and also super types and the subtypes of one specific type. I remember we can have this type of thing. Yeah, in Julia there are special values. For example, if inf for this infinity, then for this not a number, and nothing for variables with without value. And here are some exercises right here, and you have time to play with the code. Let's move on to the next level about the vectors and arrays. We have defined variables, and if we have lots of variables, it's not easy for us to handle these variables. So it is better to have this. So we can have defined arrays of vectors. We can have tuples, immutable. You can see this is quite similar to the one in Python. We can define the named tuple. You can access the t.a right here. We can also define the dictionary and also vectors and arrays. These can be called a list in Python. We can also define the different ways of using array comprehension to get the direct result like this. So special Julia can provide some functions or method. You can key, we can rand, we can generate random numbers within this range from 0 to 1, but 1 is not included. We can also generate random 5 integers within this one. We can provide the type right here. Once means we can get 5 element vector with this 1.0 with 0 also like this, and this dot is an operator. It can perform the element wise operation. Once you define this, if you define array, a vector, or a string, you can use index and slicing to get one part of some part, at least some part of element from this object. And besides this, you can also define multi-dimensional arrays. For example, this is the matrix with the 2 by 2, and this is the zeros array or matrix. This is the 4 by 4 by 4 by 4. This is the 4-dimensional matrix. It's quite large. And you can also generate a random matrix to provide like this. In Julia, it provides another function method. For example, using the this sign operator means it will do some in place manipulation on this matrix right here. Yes, this is the examples right here, and I will show it right here. For example, we 1 equals 2. We can see what's the difference. 1, 2, 3. That's just the empty space. In the this is the 1, 2, 3 matrix right here. If I provide something like this, 1, 2, and 3, this is a 3-element vector, means 3 by 1. If they call it a vector, but these two are different. If we see, we see the dot, we perform the pairwise multiplication. We will see it right here. This is we got the 3 by 3 matrix. But if we just use this, we don't use this dot operator, we see what we can get. We 1 times we 2. This is the one quite simple we got we have in the mathematics to get the 1-element vector, and this is just one value right here. Yes, take time later to get familiar with this vectors code right here. Next level, once you know how to manipulate arrays and vectors, we come to the loop and conditions. And for loops, and this iterate over all variables, for example, range, array, set, and the dictionary. So if you are familiar with other programming language, either Fortran, C, or Python, it is straightforward to know about this for loop and also the conditionals. If, elif, else. The difference is that some use elif, some use else if, some use elif. Well, but the function is the same. You gave a condition right here. You give a condition here. If the condition is true, and you can perform this command right here. Otherwise, let's skip this one to the next to make the evaluation for the next condition. Julia also provides this ternary operator, for example, A question mark B and C like this, which means that if the condition at here is true, we will take the result from this expression B. Otherwise, we will take the result from the condition from the expression C. While loop, no special for this. So if you're from the formula programming, you can always come get the same meaning. Yeah, once we have lots of variables of arrays, we are going to define functions. A function is an object that map a total of argument to return the value. This is the function in Julia. It's also comparable to the others. How to define the function? It is just use function and then name of this function and the argument, input argument, and then do some arithmetic calculation and then end. You can also define the compact form like this. They've called also called a mathematical function like this. How to call this one? Just use function name and then input the argument. Then you can get the feedback from this calling function. Yes, in Julia, the functions can also be combined by combination. For example, we have a function fx, we have a function for the gx. You can have this combination. Means we first calculate the value from this function, g function, and the output from this g function can be used as the input for this f function. You can also use this one with this circle operator like this, which means the first we will run the latter function first, and then the output will be used as input for the former function. It's the same as this nested function. Yes, some operators and in fact also be functions. For example, here the addition operator, and this is can also be considered as a function. These are the input argument to this function. You can get the result. It's the 6. And also this squared, root mean square, and the addition, they can be combined together. And these are the input for this combination functions. Like the definition of other functions, in Julia, we can pass the argument to these regular functions. We have the position argument, we have the keyword argument, we have the optional argument, and here is the example for this one, how to use this. This is the position argument and the optional argument, how to use this. And besides this, we can also define the type of this argument. It can be explicitly specified. For example, here we have a function. We have two arguments, x and y. Both x, y, we can define, give a specific type for this one. For x, it can be float 64. It can be integer 64. And for y, it's also the same. So which means that we can have one function with the function name of f, but we can have full method. Means x is float, y is float, x float, y is integer, x is integer, y is float, and then integer, this one. But we have this one function with full method. Which one will be launched if we make the call? Here, we use this method called which, and then type this, and you're going to see which one will be called from this for method. Yes, besides these regular functions, Julia can also provide more about the anonymous functions, for example, map. And map means from this variable to get the to map to another to matrix a result like this. And we take each item from from this vector and then get a new vector where this relationship. Julia has also some var args functions, means that directly it can take any arbitrary numbers argument and do them uh, arithmetic calculations. And Julia can also have the functions can be packed or chained, which means that first you have this range, and then we can have this first sum, and then the result will be used as the input to run the next function, mean squared, root mean square. And as mentioned, we have a special ending with this exclamation mark, which means that you can manipulate this array that's in place. That there's no necessary to get a new array or a new vector from this one. Okay, some basics about variables and functions, loop conditions. Then we come to the files and how to open the file. It is straightforward. Open this file and give this one a name, and then do some data manipulation. For example, copy data from this file and do some arithmetic calculation and write this result to another file, and then close this file. Yeah, open, close. This is the one pair. And also you can use open this one and do something in this file and write to another file. Julia also provides some useful functions to work with the files. For example, make dir to make this create a directory right here, and is dir to make the path if to see if this path is a directory right here, and the home directory and return to the home directory to from your working directory. So also some exception handling. For example, if you come to this error right here, I will square. Means something is wrong is right here because the squared squared root can get a negative complex number, but here it can get a real number, but here it gets a complex number. How to handle this? You can provide exception like this. Try to calculate this one. If you come to some error and catch this error and get out this error, you will see how to handle this error. So that during the calculation, there's no necessary to stop the calculation. The calculation will go on, but you know what's the problem from the code. Sometimes you can use throw to throw this error and to see what is the error for this information. I can use assert to make sure that the input value, for example, the argument for these functions, to make sure that the type of this argument is correct. Otherwise, you're not going to call this function. Last thing I would like to mention that is the scope of this of variables. This is quite an important aspect for not only for Julia but also for the other programming language. The scope is the region within which a variable is visible. Actually, it depends on where you define this variable. If you define this variable at the beginning of the program, it usually has a global scope, means you can access to this variable anywhere in this project. If you define this one in a module, it has a global scope, but just within this module. If you define this variable in a function or a macro, it has hard local. The hard local means just within this function. If you just define this for a block or a for block or which block, it's just available in this block. This is called the soft local scope. Here are quite examples. I will define this is a global and hard scope and how to access this one. If you want to change this the value for this variable, how to change it and why should you change it? You can play with the code to see how it works. Here about the some style convention, maybe not necessary to, but just to mention a little bit. Uh, Name of the variables, how to do this, and the name of a type, name of a module, and how to define name. You can give this name is understandable, not just an F. We know sometimes we can use it temporary, but from the long run, you have to give a specific meaning for this variable, for this function of the macro, so that um, when you launch, when you call these functions, or when you use the values from these variables, you know what is the meaning and which one you're going to use. Uh, ex okay, I mentioned this is a exclamation mark. This is the way to change, do the determine manipulation just in time. We also come to this one tomorrow morning. We will have this exercise about this how to write the performant code. And yes, this is the lesson part.
So, hi everyone, I am Jan Dolander de Balsch and I work at CSC. It's the Finnish supercomputing center, or well, we do many things related to IT services for kind of education and public administration and so forth. But among those things, we host the national supercomputers and the Lumi supercomputer in Kajaani. And I work as an application specialist installing software like Julia and others to the HPC machines. But regarding the course, I will present you some of the special features of Julia, things that make Julia stand out from the other languages and arguably better than, let's say, especially compared to some of the other dynamic languages like Python, MATLAB, R, and so forth. And in this session, we'll look at a little bit about the types in Julia, the type system, functions and methods, code generation, meaning how the machine code gets generated from the Julia code, metaprogramming, that's basically code that generates other code. So in Julia, that means macros, which are Julia functions that generate other Julia functions. This is also very important and kind of powerful concept. And in Julia, it's arguably implemented in the right way, which is it's everything in the Julia language itself. Unicode support, you can use arbitrary Unicode characters in Julia to in your code, writing in your code, in your functions. And then we'll have some exercises. Okay, so let's look at the types. So Julia is dynamically typed language. It doesn't really require that you explicitly declare types when you write code. Types can be inferred usually, but at some point you need to put some, well, when you call a function or something with arguments, it can figure out what those types are and can infer types. But optionally, we can also use types in the functions, but we'll see that later how that works. And the type system is crucial in order to generate efficient code, so generate efficient machine code. Otherwise, it's impossible to pass enough information to the compiler such that the compiler could generate efficient code. And in Julia, all types are defined in Julia language itself. They are this, and as a consequence, all your custom types that you define yourself are just as efficient as building types because it's all in Julia language itself. Types are also what enable the multiple dispatch paradigm. So this means that we compiler the Julia chooses the most specific method based on the argument types. And this multiple dispatch paradigm is it's what sets Julia apart from the other languages and enables Julia's composability and makes it fast with the just-in-time compiler and the LLVM tool chain. And yeah, well, look at how types are defined in Julia. Basically, we have two kinds of types. We have abstract types and we have concrete types. And then we also have a kind of a primitive type. This is something like an integer or floating point. This is just types that are plain bits. And then we have parametric types, kind of represent a set of types. Here's an example of a type tree in Julia. Here at the highest level, we have the any type, which is the super type for all types. And then one of the subtypes is this number type, which is an abstract type. Doesn't have we can't instantiate a concrete number, but it can be a super type for other types such as complex type, which happens to be a parametric type where it has, because complex numbers consist of two parts, there's imaginary and the real part. The parameter tells which type those the constituents are. For example, one concrete type could be a complex that consists of two float 64s. Then the other side we have more. This is like a whole tree of abstract types here, real types and types of like that are represent real numbers such as floating point numbers, integers, irrationals, rationals. There's a whole load of floating point numbers. Here are a few like arbitrary precision floating points numbers, the big float, and then you have float 32s and float 64s, and there are more. Similar things with integers, arbitrary precisions. Boolean is an integer. You have signed integers, unsigned integers, whole host of them. You even have irrational numbers that have a parametric type that has a symbol. Concrete representation of that is the pi number, which is irrational. And it's just kind of the irrational type that has the pi symbol here. And there are rationals and so forth. But, Julia has ability to represent all of this in the type system. That's important for generating efficient code. Let's move to composite types. These are like composite types are the way that we can create new types in Julia. And we do this with using the struct keyword or mutable struct if we want to mutable types. Here's an example of two-dimensional point type. The simplest way to define it could be just struct the name point 2D, then the fields x and y, and then we would have end. Now we could instantiate a point type. Here we didn't specify any types for the fields, but additionally we can we can give types to the fields. I will now need to create a new name for this because we can't redefine the old type. Maybe something like point2D float. And here we could give concrete types to the fields as well. Now I think if we use this, well, it will convert the arguments to the float type automatically. And that also showcases how to instantiate structures in Julia. And of course, we can access the elements of the defined types, composite types. Here, for example, the X from the point class. Okay, let's look at the constructors. This is the function that constructs the composite type, meaning creates new instances. Constructor functions, these create new instances themselves when applied to an argument tuple of a function. And each of the composite types have a default constructor, but we can also define new constructors for the types. So here's an example. I'll kill this session and create a new one, so we don't redefine, or because we can't redefine the same function or function name because they are immutable. Okay, so now we define this inner constructor. Okay, that creates him from the complex number. So this constructor takes a complex number and creates the point to the object. And this didn't work because it doesn't have a constructor for this tuple. But giving it the complex number, it will now be able to construct the point 2D. But it's possible to also define these constructors outside of the function like this. So it looks and it is a normal method definition in Julia. So now let's create the two-dimensional point. Now we add a new constructor. In the previous example, we override the default constructor, but now this will have the default constructor of the two arguments, and then we'll add this constructor from the complex number. Now we should be able to construct the two-dimensional point using both of these argument types. And the parametric types let us define a set of types. So if we want points, but we want that here the x and y coordinates would be some kind of real number. They could be any. We could define an object like this. I will actually create a new session. Okay, so now we have the point type. And it's possible to create concrete types by giving it an argument. I think we can also just instantiate a new type by giving it the arguments, and it will infer the type from the arguments like this. But also now if we give it floats, float 64s, this by default, it will figure out that it's a point float 64. But certainly you could if you want to float 32, so I guess you could do this, and we'll know how to do the promotion automatically. But anyway, this is why this kind of parametric type creates a set of types, because this could be any subtype of the real. So, and there might be arbitrary many of them. And yeah, both of these concrete types are subtype of the point, the parametric type. This syntax test, this is subtype test. The multiple dispatch enables or it supports many types of design patterns. This includes also all the object-oriented patterns, but it's more general than object-oriented. Object-oriented program is basically single dispatch, and the multiple dispatch is something more general. And the Julia approach is kind of is to build code around the type system, and this leads to a slightly different architecture than, or quite very different architecture than the object-oriented languages. But of course, compared to languages like C, they don't have any dispatch whatsoever. In the object-oriented languages, it's single dispatch because its methods are bound to a certain class usually. But yeah, maybe perhaps we are best to look at this example to get some kind of idea. So in this example, we'll define this abstract animal class. Then we will define two other abstract types that are subtypes of the animal. Abstract animal, one will be abstract dog and the other will be abstract cat. And then we will define two concrete types. One will be dog. It's a subtype of the abstract dog. Another will be cat, which is a subtype of the abstract cat. Both will have this name field, and the other will have this friendly field, and the other one will have this hunt mice field. And now we can define functions to, or we can define functions to define behavior of these types. And key to this approach is that the subtypes inherit behavior of their supertypes. So we will have this get name, which will take abstract animals. So any type that is subtype of the abstract animal, and it will return the name of that animal. We'll have this get mouse hunting ability method for the abstract cat, because only the abstract cat has this hunt mice field. You can just copy these and paste. Now possible to define a cat Billy with mouse hunting ability true, and get name Billy should return Billy. and this returns that Billy can hunt mice. As you could also create a dog. I don't have much of a imagination, so I'll create just something named dog. And perhaps something like this. Get name function should also work for the dog as well, because it's also a subtype of the abstract animal. But things like this work in Julia. And as you can see, some of these methods, they aren't written inside the structures as would be in the object-oriented languages, but outside. Okay, so a little bit about functions and methods. So functions, this form the backbone of Julia code. We use the function keyword to define functions. Each function can have multiple methods. So function really is just the name. Method is once we define some kind of arguments to the function, and then we are creating methods, and we can have multiple methods, and that's where you get kind of the name multiple dispatch. And method is, it's a function defined for specific argument types. So these arguments, for example, x and y, will have some types, and yeah, it's also possible to define it in a kind of short or block form. So this is the kind of block form for defining this sum of square functions, sum of square method. Actually, I will show you first a slightly different thing. So search for functions, we can actually define a function without methods with just using the name. This can be useful for things like documenting or creating a kind of placeholder of some kind, but then we can define methods for that function, but just by giving the arguments and doing whatever computation inside the function that we need. Now it will have one method. And also this kind of shorthand way of writing functions works as well. You will see both of these in practice. Now we can calculate this sum of squares for many different input types. If we, for example, supply things like integer and float, it will do automatic type promotion to the kind of common type. Let's try this one. It gives two complex numbers as input, and it returns a complex number as output. And here it will return a complex number with floats as the type parameter. And in our above example, we did not annotate any types for the x and y in the sum square function, and that's this is typical in Julia, that we want to avoid defining types unnecessarily, because Julia can infer those types from the input arguments and then create or then it can choose, because also here will inside the sum square function will have the function, the power function and the plus function, and they are able to dispatch on many different argument types. So Chile can just infer the type information here and then choose the correct plus and power functions to return a correct type of argument from the sum square function. So this makes the code much more generic than binding types here unnecessarily. But sometimes it is necessary, but it is mostly necessary for more kind of lower level types, but like maybe the plus or the sum, but the higher levels usually it can be inferred and keeps the code very flexible and generic. And yeah, in most cases, find omit types improves readability, or the main reason for adding types is readability to catching errors, or if we specifically want to take advantage of multiple dispatch to dispatch some argument types differently than others. Yeah, we will have this exercise here. I wonder, should we do it a bit later? I will go through the rest of the session first and we'll do the exercises later. Oh, okay, yeah, well, I will just demonstrate you this myself. Idea with is using defining the sum squared for the points that we defined previously. And if we define the point type, then we are able to dispatch the sum square with two arguments that are points and define a behavior for those. In this case, it takes the x arguments from both points and puts them in sum square, and same thing for the y arguments. And that makes us able to pass points to the sum square function. And even things like imaginary points should work. Why is it not working? Okay, that's real. There's some typo in what we did previously. We should have probably put number here. We'll need to fix that anyway. This should work, but we will have to change this to a number rather than real. Nevertheless, we can query different methods of a function using the methods function. Yeah, this is the empty function without any methods, which have some uses. And here's a small recap. Function describes what, can have multiple methods describing the how. This differs from object-oriented languages in which objects, not functions, have methods. Multiple dispatches when Julie selects the most specialized method to run based on the types of all input arguments. Best practice is to constrain argument types to the widest possible level and introduce constraint only if you know other argument types will fail. Another very important concept is concept of type stability in Julia. This is that is to that compiled specialized version of a function for its argument type, the compiler needs to be able to infer all the argument and return types of that function. And this is the definition for type stability. But it's possible to write type unstable functions like this relu function here. And reason why this is unstable is that let's see, if you give it 0, it returns integer. If we give it this floating point 1, now it would actually, if we give it a 0 like this, no. Well, it returns different types of argument types depending on the input type. In order to fix this, we would need to, rather than passing 0 here as a constant like this, we would want to use this 0 function that returns a 0 of the same type as x, because here we also return x, so that we are always returning a same output type for all arguments of the same input type. Code generation. This is hope this is not out of date, but Julia has very elaborate code generation routines. There's the kind of target independent, target specific parts. Target independent is independent of the processor architecture, and the target specific part is specific to the target processor architecture. We're going to start from the high-level Julia code that the Julia takes. It's parsed into this surface-level abstraction DAX3, and then you have macro expansors and type inferences, and eventually get the lowered abstraction DAX3, and that is fed to a code generator that generates the LLVM intermediate representation, and LLVM backend finally generates machine code. And there's also the whole loop of just-in-time loop when function is called. But that's when the code is generated, when function is first called on those argument types, unless we have, unless we have precompiled it previously. But this gives you a little bit of a overview of that, but I won't go super details on there. Maybe, or we can look at the few examples here. Actually, I would have to have these are the different functions that give you the surface level abstraction DAXing at the lowered form and so forth. You can try this yourself if you are interested in what kind of code the Julia is generating. And for performance optimizations, this might be very useful, especially looking at the LLVM and the native code that is generated. Anyway, let's go to metaprogramming. So metaprogramming, this is, so in the previous example, we saw that the Julia compiler generates this abstraction index trees. These are tree-like data structure representing the source code, and it's in Julia. It's it looks a little bit like the kind of S expressions in the Lisp language, and there's some legacy from there. And because the abstract syntax tree is represented in Julia itself, it can be programmatically manipulated within Julia as well. We can write functions that takes this abstract syntax tree and generates another abstract syntax tree. And this is basically metaprogramming, taking Julia programs or writing Julia programs that take other Julia programs and then output a new Julia program. Important for things like automatic differentiation, where we take some kind of function that computes some kind of mathematical thing, and then we would like to generate something that generates something that calculates things like gradients for that function. But here, let's look at some examples. This dumps the abstract syntax tree of this x plus y expression. And expressions, we can also use this command parenthesis to create expression objects in Julia. Similar here. Both are Julia data structures. Let's see here. We generate the expression. If we give values to the x and y, we can actually evaluate the expression programmatically, and it returns the value 4. And now we get into the macros, which are functions, but except taking arguments, they manipulate expressions, generate new expressions. This is a gist of taking expressions, which are Julia data structures, and returning a new expression. This is basically then valid Julia code. We have this, and in this example will generate these Wilkinson polynomials programmatically. Okay, so here we use the macro keyword so that we can generate macros like this with the at syntax. And now let's say we want 5-degree Wilkinson polynomials. We can use the macro, and the macro generates a function with the name that is specified here, Wilkinson and the degree. And the macro generated the expression that computes the function. So now we could supply different values here and calculate this. Yeah, this shows what the macro expands to. Here it takes variables and computes what the Wilkinson polynomial computes. Then small bit about Unicode characters. So as I mentioned, Julia has full support of Unicode characters. Some are reserved for constants like pi. If we put the backslash, write pi and press tab, it will expand into the Unicode character. And if I then press enter, you can see that there's some kind of pi here. This is actually a type of irrational pi. It's actually a singleton type itself. This type represents the value pi. It can be used for optimizing code where pi is very relevant to take. There's like a type that represents a single value. And there are other things like the in operator can also be used. We can use the Unicode variant. Maybe this would work, something like this. This would be equivalent, but it's possible to use the Unicode character. We have the square root function. It's also possible to use the sqrt as the square root symbol. Here's an example of a function where there's a lot of Unicode characters. And we can just execute it like that. I think using Unicode characters when they are reasonable, but maybe not. Maybe avoid littering them unnecessarily is a good idea, but they can be used. There are also operator signs and other things that can be very useful to use the Unicode variants for. And of course, Julia can solve the classical chicken and egg dilemma. So if we use these two symbols of an egg and a chicken, we can try sorting them. And it seems that the chicken becomes before the egg. I think we can go now into the exercises. And maybe have the lunch break as well. So as Young-Lai mentioned, I will explain you how we can develop packages in Julia and install packages and use Julia environments and things like that. Okay, so for this session, in Julia, Visual Studio Code is the kind of de facto editor for developing Julia code. You can also develop it just in the command line and using the interpreter. And then, of course, you have Jupyter Notebook. If you're familiar with that, you can run code with Jupyter. Then there's the Pluto.jl package. It's kind of a different kind of Julia-specific notebook environment that has this reactive paradigm where every time you update a value in a cell, it reevaluates all the cells. It's a slightly different to Jupyter. It's nice for certain things, especially with certain very things where you want to interactively do visualizations and change parameters to see how those parameter changes affect maybe like something like evolution of a differential equation or something like that. But I won't be showcasing them currently. I will just use the Vim editor and the command line to demonstrate the Julia packages and how to create packages and also how to install Julia environments. and so forth. But if you want, you can also use VS Code for this session. I don't have it installed at the moment, so I will skip that. But it is not somehow mandatory at all to have Visual Studio Code. Julia packages is just a directory with files with certain naming convention and nothing more. So it might be even best to do it from the command line or something like that to understand that it's just a specific set of files with specific naming convention to create packages. Anyway, let's first cover the concept of modules in Julia. So in Julia, we can use modules to encapsulate pieces of code. And modules, they have their own global scope or namespace that's separate from the kind of global namespace of other modules. And this module name main is the top level module. And we can import modules using the using statement or import, or using keyword or import keyword. The main difference between these two keywords is that using will also import all the exported names to the global namespace, whereas the import will only import the module name into the namespace. In here, example, if we had this module name, which would have this, let's say, the exported name like func and var. If we use the using, then we could use the func and the var without specifying it as a kind of the fully qualified name with module name dot something. But if we use the import, then we will need to use the syntax of module name dot func something or dot var something. And depending on, sometimes you want to use the import so that you don't collide names from one module to another, but oftentimes the using statement is what we want to use. We can try an example of creating a module. If we just start the Julia REPL normally, well, we can actually just copy paste this in the REPL. This will create this points module in the main module, and we could use the using statement like main dot points to import the names. Actually, I'll restart this. So if we have the points like here, but it's not imported, we can use this like so. But if we want to use the point, here we don't have a point in this namespace. However, we use the using points. It should, we can use the syntax. We can either use just dot points, or similarly, we could use main dot points. They are the same thing. Now we should have the point that was defined in this module in the namespace. And this is a key concept for developing packages, which will have usually a module that is named as the package name, and we can import it using the using statement. And now from this module we could use these functions and data structures. This names function will return all the names that are exported from the module. So this would correspond to the names here, point and sum square, and apparently also the module name itself. The next thing is this revise package, which is kind of handy package for developing or when developing Julia packages. Is that if we are not using the revise.jl package, then every time that we do changes in the code, we would need to reload the REPL. But if we are using the revise.jl package, then it will bring the changes into effect without having to reload the REPL, with some caveats that you can't it can't bring in changes that change constants like structure names, or if you mutate a structure or something like that, then you do have to restart the Julia REPL. I'll have a demo here. No, perhaps best to open two windows. We could try something. Well, maybe define a function. Okay. WebSub is showcase the revise.jl with the package. It should work. Maybe we should use the include at for developing script. Anyway, I will move forward to the Julia packaging. So Julia package, Julia package is just a directory with certain file names, and can look at this example.jl example package for the structure. So generally we have the package name. Perhaps if it is best that if we clone this repository, it is easiest. So the name of the directory will be the package name. It's example, and then you have the .jl. This is a convention to name it that way. If we go to inside the package, then we will have some standard files. Actually, at minimum, the Julia package will require the source directory. We can look at inside the source, and inside the source directory there will be also a file that's named similarly to the package. So here it would be example.jl, and this file should at minimum have a module that is named after the package, so example, and then some functions that it exports. The packages, well, they typically have the README and license files. These are normal, and then they have the project.toml file that is automatically generated when you add packages to, or the at least here doesn't have any dependencies, but usually there's a section with dependencies that list other dependencies that the package is dependent on. These extras and targets usually have the test package at least, or what's required for test compatibility. And then they have the fields like, actually, if I open the file, they have the name of the package, they have a universally unique identifier and a version of the package, and then they may have fields like author that have authors and the emails of the authors. And then the tests, Julia packages have the test folder. Inside the test folder, there should be at least a runtests.jl file that typically imports at least the test package and the package that the package that this repository is, so the example. And then here it uses a test macro to test the output of the functions that were exported from this library. And then Julia packages may have documentation that will be created in this docs folder, but there are separate tools for creating Julia documentation. The main tool is this documenter.jl package. This is used for creating documentation, but I will not go deeper into that. But it's good to know that that package exists. And yeah, inside the source directory, there can be arbitrarily many other Julia files that are usually included in the example. For example, in this case, in the example.jl file, and the names that we want to export are exported from there, and so forth. But let's next look at the package manager. So one nice feature of Julia language is that there is a default package manager that comes. It is a standard package and comes with the installation, and it allows you to install packages and remove packages, manage dependencies, and create isolated software environments. And we may have showcase, but you can access the package manager in a couple of ways. We can hit the is this right square bracket character, and it will see it should change into the package manager REPL, where we can use the package manager commands, and we can add new packages and query the status of different environments and many other things. But that's just a kind of convenient way to use package manager interactively. But it is package manager. It is just a normal Julia package that we can also import and use all the functions that are in the package manager programmatically, and that's also that can be very useful to use them programmatically when you do something more complicated package additions, like things like you may want to install a package that is a subdirectory in a Git repository that's a private, and maybe you want to access it via SSH. You can do things like that even from the package manager, but it is then best to use, I would say, just importing the pkg and use the pkg add, because then you can bit more easily specify what you are installing. Here is, well, it doesn't show very well, but here are a lot of different variants of installing. You can install just a package like the example package, but it can have many different targets to install, also the weak dependencies and different versions, and or installing packages directly from the from GitHub, from certain branch, and things like that. More advanced use cases that may come handy. For demonstration, we can try installing the example package. If we just use the command line, it should be pretty straightforward. Package add example, it installs the latest version of the example package. Then we can query the status of packages and see that it is installed there. Okay, it will sometimes, Julia, when you install new packages, it will want to pre-compile your existing environment. I have quite a few packages here, so it might be pre-compiling a little while. Maybe another handy thing to know when using the package manager is that these days, I think Julia can take advantage, and the package manager also can take advantage of multiple threads. So specifying something like test threads for will allow Julia to pre-compile with multiple threads. That will make things a little bit faster, especially on clusters. Okay, let's wait a bit. Perhaps I create status different wallet. That pre-compiles. That will give me a few different packages that I've installed. I've installed some data science packages here, like data frames, and machine learning packages like Flux. Then I have some Kaggle exercise that I've been doing that installed from a local path and stuff like that. This is a little bit problematic with my Zoom. It's using too much bandwidth. I will kill that. But the example packages is installed here. We should now be able to use the example package with the using statement. And then whatever functions here, it will want a string. That should work. But that is how packages are installed in Julia. Quite straightforward. Then we'll get into the concept of environments in Julia. So a good practice in software development is to use isolated environments, and that is what enables us to use different versions of packages for different projects and avoid dependency clashes. And it's a good way to ensure reproducibility, so that we use exactly the same version software environment, or we can recreate the same software environment on different computers. So let's create a Julia environment. Okay, so now we are in this directory. We'll make a new directory from the Julia REPL. Can change to that directory. No. And now if we import pkg and we call the activate function from pkg, we will activate the environment in the current working directory. Sorry, actually we need to supply path to the directory that we want to activate a Julia environment. So we use the dot, which stands for the current working directory. And now it has changed the Julia environment to the example project. If we query the status of this environment, it is empty. There's no packages here. Basically, the Julia environment is the project.toml file. This will be created by when we add package to the environment. Can add the same example package. Now it does this addition very fast because we already have installed the example package to a different location. It simply reuses that. But what Julia does, if I open another terminal here, we can go to the example project. It has created the project.toml file and added the example package as a dependency. It also creates the manifest.toml file, which is which lists like all the dependencies that are needed to recreate the exact environment that we initialized here. It will have the dependencies like the example package and all of their dependencies and versions and identifiers. Yeah, here's a bit more info. So the project.toml file describes a project on a high level, includes package dependencies, compatibilities, metadata like authors, names, versions, and it's something that we can modify by hand. And also when we add packages in environment that we have activated, then it adds those to the dependencies. Whereas the manifest.toml file, it's like an absolute record of the state of packages in an environment. It allows us to recreate identical environments in different computers, and it's shouldn't modify it by hand because it's automatically generated by the package manager. And usually Julia packages don't include the manifest.toml file in the Git, or they shouldn't, but Julia applications, which are usually the Julia package is some kind of collection of reusable components, but Julia application, that would be some specific code that you're running that can include the manifest.toml, so you can recreate the exact environment at different places. And maybe another note, when you run Julia like this, the environment that it uses by default is the default environment, and that's actually located. If you go to the home directory, there will be this .julia directory created. This will have all the packages and a bunch of other things that are installed when you install packages will be located here. And here you have packages, and you can see a whole lot of package names, and there will also be this directory called environments, and then version, and this will have the project.toml file. This is the default environment. So when you haven't sort of quotes activated anything, this is actually the project that is activated. And as you can see that the environments are simply like pointers to the packages that are installed here in this packages folder centrally. There's also other things here which we don't go into, but things like artifacts, which are, for example, packages that have binary dependencies, will install them as artifacts there. It could be other arbitrary files. And yeah, this part here is that Julia has this concept of kind of environment stacks, where you may want to install certain uh, tools like revise or benchmark tools as kind of available to you globally, but then you can activate new environments. Let's say like the example project on top of it, but the tools from your default environment will also be available. We can start Julia with this project flag to automatically activate some project. Let's see if we query the status of this package. We should have only the example package, but I think I should still be able to import this data frames package because the data frames package is installed to my default environment. Okay, yeah, I should. It's a bit of a problem because I messed up the pre-compiles. Anyway, well, here's a piece about the project.toml and manifest files, but maybe let's go to creating a new project. I don't know, this package.generate command, I don't know if it's legacy these days. I think this allows us, this packages.generate file should allow us to generate package from a template. Should generates like, yeah, this generates a very minimal package structure, and it will also add the right package name, create a unique identifier, add author name and a version, and some kind of template for the module. So that can be handy if you need to create, if you want to create a Julia package. So you should use this package.generate command. Although there's another Julia package that has a bit more elaborate templates that can also create a lot of things like GitHub actions and documentation and some README and license and other metadata files like that. But this is the most minimal Julia package that you can create with the package.generate command. And I think now you should be able to just instantiate the package. Yeah, we will want to pre-compile everything. Okay, yeah, we should activate it first and then instantiate. So activate, my package is activated. Instantiate, and yeah, that's it. Now it's possible to add that package with using our import. Oh, we can add these functions to the mypackage.jl file if we want to test how this import mechanism works, but I can already demonstrated that. Then of course, good packages have tests, and I mentioned Julia has a standard package called test that have macros like test that allows to run tests if the condition evaluates the truth, just says test pass, and I guess false will give an error. So we can look at the example.jl package, for example, for the examples. So test directory. Here we have the run tests.jl. That's the standard name for tests. It will have these tests. Let's see how we can run them. We open the REPL. Then let's see. We need to activate the package. Then we should be able to run test from the package manager. And that run the tests. That is basically how easy it is to run the tests. Also, this one-liner should work if we run the Julia with the project activated and just run the script. It will also run. So these tests can be grouped into different test sets, which just then it will print the tests when they run a bit more. Will be a bit more clarity on how they're grouped. And you can also test conditions if whether some function throws an error or should throw an error. But yeah, that is about developing in Julia. I think we can now do the exercises.